Hi, I am Shahnawaz. In this lecture, we'll introduce the critical graphs. But before that, we'll prove some results on boundness of chromatic number of a graph. So last time we did conic, and this theorem states that a graph is bicolorable if and only if it has no odd cycles. So a graph say G, this is bicolorable, I mean two chromatic, if and only if G has no odd cycles. Now the following corollary, this is the consequence of this theorem. So this states that if G is a graph, then the chromatic number of G, this is at least 3 if and only if G has an odd cycle. So this is a straightforward consequence of chromatic number of cycles. So we know that if G is an even cycle, I mean a cycle of length even, then it is chromatic number is 2, otherwise it is 3. So this result is proof this result follows from the characterization of two chromatic graphs. So this is an easy exercise. So because we know that if Cn is a cycle, so this is a cycle of length n, so its chromatic number is 2 if n is even, and it is 3 if n is odd. Now let us prove another theorem which states that so this is again a characterization of two chromatic graphs, and it states that a non-empty graph G is bicolorable if and only if G is bipartite. So a non-empty graph G is a non-empty graph is bicolorable or two chromatic if and only if it is a bipartite graph. So let us prove this result. So by a bipartite graph, we mean a graph, so we say a graph G is bipartite. Suppose we have a graph G with vertex set V and edge set E. So we say this graph G is bipartite if this vertex set V can be partitioned into two disjoint subsets, say V1 and V2. So their intersection must be empty, and these both sets V1 and V2 they must be independent, i.e. No two vertices in V1 are adjacent and no two vertices in V2 are adjacent. Then in that case we say G is bipartite. Let us give an example here. So suppose we have a graph G on 6 vertices. So these are the vertices V1, V2, V3, V4, V5 and V6. Here this is a set V1, this is a set V2. So they have to be independent. I mean there is no edge between these vertices V1, V2 and V3, and no edge between the vertices V4, V5 and V6. And any edge of G has one of its end vertices in V1 and another vertex in V2. So let us suppose our graph is like this. So this is our graph. So one can note here this set V1 is independent and this set V2 is also independent. Now to prove this result, let us first assume that this graph G is a bipartite graph. So prove. So let us consider, so let G be a bipartite graph. We have to prove G is 2 chromatic. Now if G is bipartite graph, then its vertex set can be partitioned into two disjoint independent sets. So let G be a bipartite graph with vertex set V. Then V can be partitioned into two non-empty disjoint independent sets. Now by independent we mean a set in which no two vertices are adjacent. I mean there is no edge whose both end vertices are in the same partite set. Into two disjoint independent sets, say V1 and V2, such that V is their union. Now by this square cup I mean the disjoint union. So this is a symbol that we use when their intersection is empty. So this is the disjoint union. Now what we will do, we'll assign one color to V1 and another color to V2. Now assign color, say color 1 to V1 and I mean we have to assign color 1 to all the vertices in V1, to all the vertices in v1 and color 2 to all the vertices in v2. So this will provide a two coloring of G. This gives a two coloring of G. Now since G is non-empty, so it is chromatic number must be 2. Therefore chi of G is 2. If G was an empty graph, then it is chromatic number would have been 0. Now let us prove the other direction. So conversely let us consider G to be bicolorable. Let G be bicolorable. That is G has a two coloring. Now what we have to prove, G is bipartite graph. That is, we have to partition V vertex set of G such that we have to partition its vertex set into two disjoint independent sets. So denote the by V1 the set of all those vertices, the set of all those vertices which are colored, say colored by 1, which are colored 1, and by V2 all those vertices of G which are colored by 2, Now obviously two vertices get the same color if and only if they are non-adjacent. So in V1 we have all vertices of G which are colored by this color 1. So that means all the vertices in V1 are non-adjacent to each other, i.e. this V1 is an independent set. Similarly this V2 is also an independent set since it contains all vertices which are colored by 2. So that means this G has a vertex set V which is partitioned into two subsets V1 and V2 which are independent. So clearly V1 and V2 are independent subsets of vertex set of G. Therefore V1 intersection V2 and V1 intersection V2, this has to be empty. So this is empty. So therefore G is a bipartite graph. Now let us move towards the critical graphs. So we have the definition. So let us consider a graph G. So let G be a k chromatic graph. So G is given to be a k chromatic graph. If chi of G minus V. Now by G minus V we mean a graph subgraph of G which is obtained by deletion of this vertex V. I mean this G minus V is a graph which is obtained from G by removing this vertex V. So if chromatic number of this graph G minus V is k minus 1 for any vertex for every vertex V in G, then this graph G is called k critical. Then G is called k critical. So this is called a k critical graph. Now let us give an example of a say 4 critical graph. So let us consider a graph on 7 vertices. So this is an example of a 4 critical graph. So suppose we have a graph like this. So these are the 6 vertices. So this is 4 critical. That means its chromatic number must be 4. So let us give a coloring of this graph. So let us color this vertex by red and this by red. Now these two with blue color us color these two by green color. So one can note here it's a 3 cycle, so 3 colors are to be used. This is again a 3 cycle, and this also a 3 cycle. Now this vortex is a remaining vortex, so we can color this vortex. Let us paint this vortex by this color, cyan color. So it is chromatic number is 4. So this is our graph G. So we say it is a 4 critical graph. That means it is chromatic number must be 4. So one can note here it is chromatic number is 4. Now if we remove any vertex here, any vertex, it is chromatic number should be equal to 3. Now if we remove this vertex, so one can observe here we are left with 3 colors, red, blue and green. Now let us remove this color here, let us remove this vortex here. So we'll draw this graph again. So this is this vertex. So we have removed this vertex, so these edges are gone. So we have these edges remaining. Now it is chromatic number must be equal to 3. So let us give a coloring to this graph. So we can color this vertex with a red color, with this vertex with red color. Let us paint this vertex with blue color, this with blue, this with blue. So for we sorry, we cannot use blue color here. So now let us take the green color, let us paint this vertex with green color and this with green color. So this gives the coloring of this graph. So it is chromatic number is reduced by 1. Same is true with every vertex here. So if one can remove this vertex, we get another subgraph of this graph which is also 3 chromatic. So this is an example of a critical graph, 4 critical graph.